very important. Without buffers, you would die. Our blood is a buffer because what a buffer does is it absorbs acid and minimizes changes in pH. Inversely, it absorbs base and minimizes changes in pH. So a buffer solution is a solution that keeps pHs from changing by large amounts. It resists changes in pH. And it does that by having ions that mop up hydronium or mop up hydroxide as they get added. Buffer solutions are usually a weak acid and its salt. So if we look here, ethanoic acid is a weak acid. And in water, we know that ethanoic acid looks like that. So this is a weak acid and its conjugate salt. That negative ion is a salt because we could assume that there's a positive ion to go with it. This solution right here, this weak acid solution, behaves as a buffer because there are ions present that if you add hydronium or if you add hydroxide, it will absorb them, it will react with them, and keep them from changing the pH. Does this kind of make sense? Maybe? Okay, so if I add hydroxide to this solution, this part of it, the acid part of it, reacts and makes more of the ion and water. So this is adding base. The weak acid reacted with the hydroxide ions and made salt and water. So what should have made the pH go up has now hardly changed the pH at all because this is a neutral solution over here, what was made. Inversely, this same solution, if I add hydronium to it, the salt reacts with that, with the acid, to make weak acid, and water. So what should have made the pH go way down has now minimally changed the pH because I've made weak acid, which has a higher pH, right? And water. So what a buffer does is it takes things that should have drastically changed the pH and minimized it. Made it to where the pH doesn't change a whole lot. And that goes back to, without buffers, you would die. Well, our blood is a buffer. So if something gets in your bloodstream that is very, very acidic or very, very basic, your blood does its job and it doesn't allow the pH to change very much. Because our blood needs to be a certain pH for us to perform bodily functions. So that buffer action keeps us alive, basically. Because we drink orange juice, we drink soda, like our body ingests all kinds of acidic and basic things, sometimes to extreme amounts, and your blood buffers it and keeps you from dying, basically. Now, there's a limit. It's called buffering capacity. Your blood has a buffering capacity. You can only ingest so much before your blood changes pH and you die. But it does a really good job for a really long time. Does that make sense? Just a little bit? Okay, so this is called mopping up, which is not really a scientific term, but you add base, the weak acid mops it up, and minimizes changes in pH. The same solution, you can add acid, the salt mops it up, and minimizes changes in pH. All that same solution, you can add acid or base, and the pH doesn't change very much. Water is not a good buffer. You add acid to water, it immediately plummets in pH because it doesn't mop anything up. You add base to water, the pH immediately rises. Buffers keep changes in pH from happening. Okay, hold on, let me erase. Okay, the pH of buffers. The pH of a buffer solution is determined by the pKa or pKb of the weak acid or base and the ratio of the concentrations of each component. To calculate the pH of an acidic buffer, use Henderson-Hasselbalch, either for acidic or basic. So the pH is equal to the pKa of that weak acid, the negative log of the Ka, plus the log of the concentration of the salt present, that's the negative ion, divided by the concentration of the original weak acid. Inversely, for a weak acid or a weak base buffer, the pOH is equal to the pKb plus the log of salt over base. And then if you want to know the pH, remember pH plus pOH equals 14. Questions? Okay, I'm going to stop there. That's your intro to buffers.